Earlier, we discussed about substrate induction and catabolite regulations of metabolic pathways. So now let's discuss about feedback regulations. So feedback regulation is one of the more well-known types of regulation. And unlike substrate induction, where the inducing element is the substrate, which is the reactant at the start of the pathway, or even the catabolite regulation, whereas it's one of the intermediates or even a byproduct of the metabolic system per se. In feedback regulation, the end product of the metabolic pathway is the one that controls the pathway. So the one of the most well-known is feedback inhibition, whereas the activity of the enzyme, usually it's the first enzyme of the pathway, is inhibited by the end product of that specific pathway. So how do they do that? There are two major ways. So you have allosteric inhibition, whereas your inhibitor, since it's the end product, it's of course very different from the substrate. So it doesn't, based on our lock and key model and even your induced fit model of enzymes, of course, it doesn't resemble the enzyme substrate. It doesn't bind to the active site. The inhibitor here binds on a different site. So it still binds to the enzyme, but on a different site from the active site. And that induces a change in the enzyme such that it inactivates it. It doesn't bind to the substrate anymore. Or you can have isostate inhibition, or although this is a bit rare, so the inhibitor resembles the substrate. So since it is for a feedback inhibition, it's not very common that the end product of your pathway resembles the starting product of that pathway. So anyway, so those are the two possible ways how feedback inhibition works. And then we also have feedback repression. So in what's the difference between them? Although it also has a negative control, or it does a negative control to your metabolic pathway. For repression, you are inhibiting the synthesis of the enzyme. In inhibition, you are just inhibiting the enzyme per se. So the enzyme is already present in feedback inhibition. It's just that you make it inactive. Whereas in feedback repression, it's the gene that you inactivates. Therefore, the enzyme cannot be made. So the enzyme itself is absent. So those are two ways of feedback regulation. So we have many diverse types of pathways, and some of those pathways are branching. So there are several types of feedback regulations happening. So or rather, specifically for this one, this is a feedback inhibition. So consider this pathway, you have a branching pathway. So metabolite 1, this is the starting substrate, and enzyme 2 is, let's say, it's the start, it's the beginning of that pathway. So it's the enzyme that catalyzes the reaction at the start of the pathway. And then moving on, and at metabolite 3, your pathway branches into 2. So you produce metabolite 4 and metabolite 5 into 2 separate ways. So each of them produces a product, so 2 different products. Now, in concerted feedback regulation, the second, or rather the enzyme responsible for the first reaction, enzyme 2, the E2 here, it is inhibited by both P1 and P2. So the end product is inhibits enzyme 2. And what do you mean by both inhibits? That means both P1 and P2 must be present to inhibit enzyme 2. So that is for concerted feedback regulation. So if only P1 is present, it has no basic effect on your enzyme. So there's no inhibition. Or even if only product 2. Likewise, if only product 2 is present, it cannot inhibit enzyme 2. So both of them must work together to inhibit enzyme 2. So that's concerted. And then we also have a different method, or a different version of that. So again, the same branching pathway, except that this is a cumulative feedback regulation. P1 and P2 singly, by themselves, can inhibit enzyme 2, but only at a certain extent. So, for example, P1 can inhibit enzyme 2 at, say, 40%. So, it lowers the activity by 40%. And then P2 lowers activity by 30%. So, that is cumulative feedback regulation. So, by themselves, they can partially lower the activity of the enzyme. However, if both of them are present, they have a greater effect, just like concerted. But unlike the concerted inhibition, where both of them must be present to actually inhibit them by themselves, for cumulative, by themselves, they can inhibit it only, but only partially. And then we have a compensatory antagonism of feedback inhibition. So this one is a bit, looks a bit complicated. So it actually involves inhibition of the inhibitors. So how does it happen? So for example, you have here a metabolic pathway that branches out into two. So at your metabolite D, so you have the starting substrate A, enzyme 1, enzyme 2, enzyme 3. And then you have, when you produce the metabolite D, it branches out. So metabolite D can be used to form metabolite E, or it can be used to form metabolite G. Now, the complication here is metabolite G is one of the reactants, or also metabolite G is also a metabolite, an intermediate in a separate pathway. So it's a different pathway, this pathway, and we need this pathway needs G to produce your F and other F, G, H, I. So let's say I. So I or J or K. So any other metabolite product for another pathway. Now, the complication here is your product, one of the product of the branch pathway, particularly this one, H, is an inhibitor of your enzyme 1. So if in the presence, or if there's a large amount of H, the metabolite or the product H, enzyme 1 is inhibited, therefore your the whole pathway shuts off. However, there is a however. However, since this pathway is involved with another pathway, so if you cannot, if the pathway stops here, you cannot produce G, and G is needed by another pathway. So, if your H inhibits your enzyme A, there is no G that will be produced, and therefore what happens in the separate pathway, since there is no G, your K accumulates because there is no G to react with E to form your product F. So what happens in the accumulation of F, your K in the accumulation of K, your K now inhibits the inhibitory, or rather it negates the inhibitory effect of H. So it somehow like inhibits the inhibitor H, something like that. So you have now, it inhibits the inhibitor, therefore the reaction can proceed so that you can form product G. So that's a compensatory antagonism. So this allows the pathway, this separate pathway, to continue on even though you have overproduction of H. Although since this is a branch pathway, it doesn't necessarily mean always that there's always H here. It can be that we can divert, they usually divert the pathway towards here. But anyway, that's for your this mechanism, compensatory antagonism of feedback regulation. Now, we also have sequential feedback inhibition. So this is a simple branch pathway. So in sequential feedback inhibition, in the branch pathway, you have two end products, F and H. F is an inhibitor of the enzyme here, and H is an inhibitor of a different enzyme. So the pathway branches out. So for this one allows, this type of inhibition allows, for example, in abundance, if F is abundant, it doesn't F doesn't need to be made. Therefore, F inhibits this enzyme, so it stops the production here, but you can still continue on with the production of H. And vice versa, you can do that. In the abundance of H, you can still produce F. Now, it becomes sequential because, for example, if there's high amount of F, at the same time there's also high amount of H. Both of them inhibits the enzymes at this point, so your pathway stops at D. So since there is no enzyme, or the enzyme here is inhibited, now there's now an accumulation of D. And now D can be used to stop the first enzyme of the pathway. So the whole pathway itself stops. So in this type of mechanism or layout, your you can rather, the control here is that you can still produce one of the products of a branch pathway even in the abundance of the other product. But you can stop the overall production if both are abundant. And the good thing here is that we usually stop the first enzyme. In this case, they just stop the enzyme at the branch point so that the other branch is not affected. So that's for sequential feedback. So we also have isozymes. So isozymes, so for example, consider another pathway. So you have branching. So you produce multiple different products, H, G, and E of the pathway. So these products have inhibitory effects on the enzymes, catalyzing A to B. Now, the only thing here is we have isozymes. Isozymes are enzymes that they are slightly different from each other. How so? For example, we have isozyme, say isozyme 1, that catalyzes A to B, and it is inhibited by H. So this isozyme 1 is inhibited by H, but it is insensitive. It doesn't respond to E or it doesn't respond to G. It only responds to H. And then there's another isozyme 2, that only responds, for example, to G, but doesn't respond to E and H. So those are isozyme regulatory control. So in this case, we usually see enzymes or rather isozymes at different compartments in a cell. They are not always present on a single compartment. All isozymes are present on a single compartment. That's not the case. We usually see them on different compartments or organelles inside the cell. So you have that. Okay, so we also have amino acid regulation for RNA synthesis. So you have here guanosine tetraphosphate, PPGPP, and you have guanosine pentaphosphate. So it helps stops RNA synthesis when you are missing certain amino acids, because it's important to actually your cell cannot produce proteins if it is missing just one of the 20 amino acids. That's why you have the essential amino acid. It's actually quite important. So you have your since you are missing an amino acid, you do not want to transcribe anything. So the thing here is that in your PPGPP can sense the absence of your amino acid, or there's a missing amino acid, so it actually stops the production of nucleotides, especially GTP nucleotide. So that if you cannot produce GTP, you cannot transcribe anything, or even you cannot even replicate anything. So that's amino acid regulations. So another regulation that we have is energy charge regulation. So this is based on the levels of ATP you have in the cell. So we have equation here. So we can loosely estimate the energy charge within the cell by getting the concentration of the ATP plus 1/2 ADP over the total amount of the adenosine phosphates. So you have ATP plus ADP and AMP. So how does it usually work? So your cells, as I mentioned before, can sense the concentration of cyclic AMP, which is basically the isomerized form of adenosine monophosphate. So AMP. You have your in the processing of ATP. So the general reaction is ATP to ADP, and then you produce. There's energy reaction here. So ATP to ADP. And then the ADP, if you input energy, you will recreate or regenerate your ATP, usually through catabolic reactions. Now, your ADP, so if there is there's a limited supply of energy, or say glucose, sometimes you can still regenerate ATP from ADP. So you get 2 ADP, transfer one phosphate to the other, you will get one ATP and another AMP. And that AMP can form your cyclic AMP or AMP kinase. So this is a signal now for the production. So that means we are lacking ATP. We need to produce more ATP. So it's a signal to create more ATP. So it's a signal to activate catabolic reactions. And it's also a signal to stop anabolism, because anabolic reaction consumes a lot of ATP. So that is one of the signals. So if there's a lot of ATP, ATP inhibits the MP kinase, and in turn, so you do not have a signal here, so it will shut off the signal that induces you to produce more ATP. At the same time, it enhances ATP consumption or the anabolic reactions. So that is energy charge regulation. So another type of control is permeability control. It allows you for usually this involves cells that have compartments. So eukaryotic cells, they are well compartmentalized. So they restrict certain reactions to certain organelles or certain vesicles. And by doing so, they can actually control how the their metabolism works. So we have different ways of allowing nutrients, metabolites, substrates inside the cell. So we have the passive transport and even your carrier transport. So we have facilitated diffusion, active transport, or group translocation. So here in permeability control, it usually involves the presence of carriers, or rather your channels. So one good example for that is your glucose transporter. So the insulin-based, I will link another video if you to look at how insulin can control the glucose transporter inside the cell. And in doing so, it also allows control of energy, or rather energetic control in the muscles, especially in the muscles. Okay, so that's for metabolic control. So in the next video, we will be discussing about regulatory mechanisms for overproduction of primary metabolites. So basically, we already discussed how these cells control their metabolism. In the next video, we will be discussing how metabolic engineers utilize those controls in order to suit their own needs.